Very critical problem related to Atwood's machine. The Atwood's machine system, there are two pulleys and a common rope, which is clamped with the ceiling, and holding the pulley to it's proceeded, and it gone through the pulley one, and it was attached with an object weighing 200 Newton, and another pulley holding an object attached 300 Newton. So the question asked us to find the T1, T2, and the acceleration of the whole system, like the objects, the acceleration and its direction of or the magnitude of the acceleration, that at like what acceleration it will walk. Actually, why this question asked for the acceleration? Because this pulley 2, it is said in the question that this pulley 2 is portable and it's movable, so it's moving, right? Due to the 300 Newton, it's moving, and this pulley 1, it's clamped to the ceiling, so it can't move. It's still, but it's moving, it's portable. So we have to assume an acceleration. We don't know still in which direction the acceleration will walk. Some people will just think, and from their common sense they will say that it's in the favor of 300 Newton, the direction of the acceleration will go downwards. So because this is 300 Newton, the object swaying 300 Newton is greater than 200 Newton, but actually it's not, we can't tell that actually, because we will figure it out later. I don't want to spoil that. We will figure it out later in the solution. So let us assume a direction of the acceleration. Let us assume that the direction of the objects is in favor of 300 Newton downwards, and in against of the 300 Newton object, the acceleration of 200 Newton object acceleration is upwards. Okay, so if it's going downwards, it will go upwards, because it's a common rope. It's going downwards, so it's going downwards, so it's taking the common rope along with it. So the common will basically go up, and it will go down. So if we just imagine it, right? So let us just this, yeah. So acceleration 2, and okay, just this is acceleration 2, and this is acceleration 1. All right, so now we have to get our tension directions figured out. So this the object is the object's weight is directed downwards, so the tension will directed upwards. Similarly, the weight of the object is directed downwards, so the tension of that second object is also the opposite. And now here from our basic sense, we will try to derive the equations. So if the 200 Newton is working downwards and the acceleration is upwards, the tension is upwards. So T1 minus 200 equals m1 multiplies a1 or a1. We have to tell it a commonly because we still don't want to divide the acceleration. We want to tell it as, we want to represent it as a common acceleration. We will divide it later in the solution. So for the second object, the 300 Newton is weighing, it's walking downwards, so due to gravitation and in favor of gravitation, so 300 minus T2 equals m2 multiplies a, right? This is equation 1, this is equation 2, and this is equation 1. Okay, so now there is a problem actually with the acceleration due to the length of the common rope. Why? You see that the common rope is clamped and it's proceeded, it's holding the pulley 2, it's going through the pulley 1, it's connected with the object 1, and the pulley 2 is weighing the object 2. Here if you can see that the common rope, the length of the common rope here before the pulley 1, in this part, actually in this part, my highlighted part, this part, the length of the common rope, and in this part the length of the common rope are different, right? Both lengths are different. That here it stops at the pulley 1, there is a length. It starts with the pulley 2 and then the pulley 1, there is a length. Here it starts from the pulley 1, ends up to the object, so there is another length. So let us assume that it's L1, starting from the pulley 1 to the object, it's L1, the length of the rope, and let us assume that there's a L2 length starting from the pulley 1 ending to the pulley starting from the pulley 2 ending to the pulley 1, and there is a L3 length starting from the ceiling ending up to the pulley 2, L3 length. So if we can tell by our common sense that we can say that this L3 is equals L2, it can be equated equally. Why? Because the figure is drawn like that actually, so it has to be like declared by our common sense. Figure it out by yourself. It will not be mentioned in the question actually, so you have to figure it out. So now the L2 and the L3 are equal, so we can say that this is L3, this is L2, whatever you can say, you can say and tell it's L and this is L1. Let us now write another equation, another part, that L1 plus L2 plus L3 is a constant. It's not false, it's not false, it's true. I'm not lying, it's not false, it's true. So it's a constant, right? So it's logical. L1 plus, we knew that L2 is equals L3, so we can say that 2L2, we can say it's not false, still it's equals constant, it's equated constant, it's not false. If we differentiate it, in respect differentiate it in respect of t. If we differentiate it in respect of t, then it will be converted to velocity. The displacement will convert it to velocity. v1 to v2 equals 0. The constant is differentiated, so the answer will be 0. In right hand side, it's not false, it's true. I'm not lying still. So if we differentiate the velocity again, we will get acceleration a1 plus 2a2 equals 0. I'm still not lying. Then a1 is equals minus 2a2. I'm still not lying. It can be equated to minus 2a2. It can also be said that a2 is minus half of a1. Now we got these two things. This is the main thing. The length of it is due to the length of the rope. So it happened due to the length of the rope. The acceleration are divided for to each pulleys, or like two separate objects. The acceleration are different due to the length only. And now if you notice another thing, that for the tension T1 and here the tension T2, it's a common rope, right? So if the tension is T1, this rope is following the same rope which weighing the pulley 2. So this T2, the tension against the 300 Newton object will be equated to twice of T1. Why? Because this is a length, this is another length divided at the same pulley. The pulley is in the middle, it's divided due to the pulley. The length here is L3. There is another tension, but the common tension, this is another tension, is divided. The tension here is divided here due to the length, and here is the tension 2 for the second object. So we can easily tell that L2 is equals to L1, right? This is important. So these three things are the fundamentals. Now if we okay, don't actually need it. If we now divide 1 by 2, the equation 1 divided by equation 2, then we'll get that T1 minus 200 divided by 300 minus T2 equals equals M1 M1 multiplies A divided by M2 multiplied A. Yeah. Now if we replace this T2 with oh sorry, here I have to T2, it's T2, sorry, it's not L1, it's T2 equals 2T1. So if we replace T2 with 2T1 minus 2T1, and here these acceleration are not the same, so we have to replace it as well. M1 with A1, M2 with A2, right? Now A1 is equated to 2A2 minus 2A2, minus is the direction and A2 is the value. So A2, it's 2A2, right? Now if we write the next line, then it will be T1 minus 200 divided by 300 minus 2T1 equals M1 2M1 divided M2. Now if we write the next line, then we have to calculate. Basically there's only T1, we know the value of 2M1 by 2, we can get that value. So 2M1 by M2, so we know the M1 and the M2. Here the M1 and the M2 is derived by dividing it with the gravitational constant, 200 by 9.8 and 300 divided by 9.8. They are derived from here. Actually it was not given in the question. So T1 minus 200 divided 300 minus 2T1 equals 2M1 divided by M2 is let me calculate it. 2M1 divided by it's 1.33. Then if you wanna there's only one variable which is T1, so it's easy to get the derivation. So if we calculate the T1, it's basically 163.66 Newton, 63.66 Newton, and the T2 is 2T1, so it's 2 multiplies 163.66 Newton equals 327.32 Newton. Now the T1 is derived, but T2 is derived, but what about the acceleration, right? Now we got the T1 and the T2, so we can satisfy our, if we can satisfy the value of T1 or the T2, we can take it whatever we want. We can, whatever equations we choose, we can choose. Okay, now the question is, in which equation we have to satisfy? If do we have to satisfy it in this equation? No. Why? Because the question wanted us about the question asked us about the common acceleration, not about the A1 and A2s. We don't want the A1 and A2 separately, we want the common acceleration. The common acceleration is this. Either we have to satisfy our T1 here to get our acceleration, or have to satisfy the T2 to get our acceleration. So let us take any one of them. So I'm taking the T1 actually. So the T1, if we satisfy our T1, the value, so that the T1 is 163.66, 163.66, and the m1 is 20.41. Now the acceleration will be minus 1.78 meter per second square. So this is so this is the value of acceleration. These are the values of the tension. So these are the answers. Now the question is, why the acceleration, why we can see that actually the acceleration, the second acceleration, or the first acceleration is twice the second acceleration, but in the negative direction. So by this equation only we can tell that the acceleration is working twice the acceleration of the second object, but but not upwards, but it's downwards, right? So it's working downwards. So actually this direction will not be the same. It will be directed to opposite, and this will direct it to opposite. So this is the actual direction. So sometimes in real life, sometimes there could be some objects which can weigh more than an object, but if you are able to place that in a mechanism or in a function that the length of the common rope is divided, through which the length of the common rope is divided, then you can actually change the acceleration, right? So here we can prove that mathematically. You can do it physically if you want. It's very important for engineering, and it's a very critical and technical question for Atwood's machine. So it will be very helpful for your college lectures and upcoming exams. So it's very important. And where here we can also see that it's negative, so we can predict its direction. And why the tension, the logic of the tension is that only the length. So the focus, the answer is not actually the T1 and the T2 and the A. My objective was to make you explain that or teach you that the pivotal point of this concept, the Atwood's machine, is not only limited to some deriving tensions or accelerations or what. You have to think it very from the very root point. So the length, actually, from the conclusion is the length might also be a factor solving this Atwood's machine problems. The length might be a factor also.